Okay, chapter 1. There, I said okay. Chapter 1 talks all about transformations, reflections, stretches, shifts, vertical, horizontal shift. Okay, that's what the whole chapter is about. And so, this is your standard equation with all the basic transformations in it. Okay, so this is if we had combinations of all the transformations in like a normal, say, polynomial equation. Okay, so we know these and they still all apply, but we can list them out again. This A, he represents a vertical stretch. Okay. And it would be A times your, what's wrong? Oh, I thought there was something on my head. Vertical stretch is taking your y values and multiplying them by whatever A is, right? So it'll be y, or maybe I should say A. I don't want to put in, hold on. A multiplied to y. Okay, and we also have to remember that if there's a negative in front of A, that means that there is a reflection. So if A is negative, it's a reflection on the x-axis. So meaning the x-axis is the mirror, but all your y's turn to the opposite sign. So y's are opposite. Okay, so if it was a -3 before, it turns into a 3. Okay, this B, this is the horizontal stretch. And remember, whatever number is there, it's actually doing the opposite. So if there's a 2 there, it's cutting all your x's in half. Okay, so it would actually be like 1 over A multiplying to your x's. So if there's a half there, then all your x's are going to be twice as big. What's up, Kyle? F is just part of the standard equation. Like this is just because it's a normal polynomial equation. Yeah. And your hand-ins are corrected. They're handed in. So then, also, if A is negative, then it's a reflection on the y-axis. Oh, sorry. I said A. Oh, yeah, these should be B's, correct? Yeah. I'll switch him to a B, him to a B. Okay, so if your B is negative, it's a reflection on the y-axis. So that changes x's to opposite. Okay, your H is always your horizontal translation. And that means left or right. So it's going right if it's negative. So if it's negative, it's right. If it's positive, it's left. And our last one is our vertical translation. If it's positive, it's up. Negative, it's down. Section 7, or not 7, 1.4 talks about inverse. Okay, so the inverse, if a function, it says if f is a function domain A and B range, the inverse, if it exists, is when the B domain is B and range is A. So basically the inverse means you're taking your x and your y's and you're swapping them out. So if I had a point of, let's see, 5 and 4, this is my normal point. The inverse, and I'll just call it this, the inverse is usually with a negative one, it shows up at the top. It is then 4 and 5. It's just taking your x and your y and you're switching them. Okay, so that could be a set of points. It could be a picture on a graph and writing out all the points and then switching them and drawing the new picture. Okay. One thing that we talked about was a horizontal line test. So it says if it is possible for a horizontal line to intersect the graph of a relation more than once, then the inverse of the relation is not a function. So if I had a picture like this and I drew a horizontal line and I touched in 2 spots, then the inverse is not a function. Okay, so in this one I would say the inverse is not a function. Because if you think, if we were to switch these points, the picture would turn, and usually we test functions by doing a vertical line test. So if we did a vertical line test on the switched one, it still would not be a function. Okay, so this is just a way of taking an original picture, and then if you draw a horizontal line and it touches more than twice, then the inverse of that picture is not going to be a function. And we also did inverses when we had equations, right? So if we had an equation, f of x is equal to 3x plus 6, f of x always represents y, right? So if this was actually written as y equals 3x plus 6, if I wanted the inverse of this equation, I would switch my x and y and then solve to get y by itself. So I would write it as x is equal to 3y plus 6, and then I would solve it. So I would minus 6 over, so I have x minus 6 equals 3y, and then I divide by 3. And this would be like 1/3 x, and minus 6 divided by minus 6 divided by 3 is a minus 2. Chapter 2 is radical functions. So we're talking about equations that have a root sign in them. And basically, we will still be doing transformations. Okay, so I don't know where I just left off when I was talking, but this is your typical standard root equation. That's as easy as it gets, okay? And we have to remember, roots we can't have what underneath? What? Negatives. Like what? Yeah, no negatives. Okay, so there is no point in us putting negative things under the root because it's just going to be undefined. Okay, so if we were picking x's and y's, if my x was 1, the square root of 1 is 1. Okay, if I usually try to stay with perfect squares just because it works out. If I picked 4, the square root of 4 is 2. And then the square root of 16 is 4. Okay, and so what your picture starts to look like is 1. Oh, and if this was, we can also have 0 in there, right? Because if we had 0, our y would be 0. Okay, so our points are going to be 0 and 0, 1 and 1, 4 and 2. And then if we went 16 and then 4, our picture would start to curve like this. Okay? So it's not going to be in the negative area. So if our typical normal root equation is this, then the transformed one that has any possible transformations on it is going to look like this. Okay, and all the A, B, H, and K are all going to be the same thing and do the same things that they do to any other equation. Okay, so if we were graphing, this is an example on page 80, if anybody's following with me. It says that we want to graph the normal, just straight line equation, 3 minus 2x. And we also want to graph it as a root equation. So all they're saying is you're taking the equation of f of x and you're putting it under the root. Okay, so we know how to draw a straight line. They, in the book, use a table. You can use a table with points and just plug in to find x's and y's, but I always like doing the y equals mx plus b form, because this is already in that form, it's just backwards. So if I wrote this minus 2x first, and then the positive 3 after, this is always our y-intercept, and this is our slope. So I can draw my diagram starting at my y-intercept of 3, and then that means this is my rise, and since there's nothing under the negative 2, we'll put a 1, and that would be my run. So my rise is actually falling 2, so I'm going down 2, and I'm running 1. And so my point would be there. Okay, and if we wanted to see where it's actually crossing on this x-axis, we could just put 0 in for y, and we'd have minus 2x plus 3, and we minus 3 over, and then we have a minus 2x, and we divide by minus 2, and we end up with 1.5 equals x. So that means it's crossing at 1.5. Okay, so now if we wanted to do the root equation, we can do the same thing, but we just do points with this as our equation. So we can make a table if we want and graph the picture. So if, hold on. Okay, so we can graph our line like that, but it might be helpful in this situation if we use a table. So this is our equation, and if we create a table and we just choose x's and we plug in for y, so if we, let's just say I'll choose some negatives, a 0, and we'll go from there. So if I put negative 2 in for x, I get 4 plus 3 is 7. If I put negative 1 into the equation for x, so I would be putting it in here just in case, we would get 3 plus 2, that's 5. And we keep filling the table out. If x was 0, then we're left with 3, and if x is 1, then we're left with 1. And then I want to use my x-intercept point just to make sure I have it, because I have a y-intercept point on here. And remember when we were drawing it, we let y equal 0, and then we solved, and we found out that when y was 0, our x is 1.5. Okay, so these are our points for our just our line, and we could graph them and it would just make a straight line, just like the one we just did. And now, if we wanted to do the root one, our x's all stay the same because we randomly picked them. And what happens is our y's are going to be the same but the root of it. Because if we put -2 in here, we would have -2 times -2 is 4, plus 3 is 7, but now we have a root sign. So it would just be root 7. So all our y points are just going to be the root of our original ones. So this will be root 5, root 3, and the root of 1 is 1, and the root of 0 is 0. Okay, and you'll notice these points stay the same on both of the graphs. Okay, anybody remember what those points are called? Good, because I couldn't think of it. Invariant points. So if we were graphing it, these points, let's just, if I drew, say our line was like this, then those points show up on both of our pictures. So then your radical one would look like that, roughly. Okay? So if I look at example 2 on page 92, it's solving radical equations. And basically all we're doing is solving for x. So if I have something like this, I might want to start with saying, like, do I have any restrictions or non-permissible values? So anything under the root, remember, can't be less than 0. So if I had x plus 5 has to be greater than or equal to 0. Okay, so then if I solve this, I would have to say x has to be greater than or equal to -5. Okay, because if I put -5 in there, -5 plus 5 is 0, and that's okay. But anything like -6, -7, anything like that would make it a negative under the root. Okay, so this would be the non-permissible value, or the restriction. So first, if we're going to solve this equation, we want to get rid of the root. So to get rid of a root, we square. Okay, so squaring and rooting cancel, and we have x plus 5 equals, and this is a FOIL situation. Don't get tricked. Okay, so we actually have to FOIL these two brackets. So we end up with x squared plus 6x plus 9. So once we have this, we probably want to get everybody together, and then hopefully we can factor it. If we can't find factors for it, what would we have to use? Yeah, quadratic equation. We could use decomp is only if there's a number in front. Otherwise, it's just factoring. Okay, so I get a minus the x and minus the 5 over. So I have x squared plus 5x plus 4. Okay, so I'm going to try to look for a factor first before I use quadratic formula. So is there anything that multiplies to 4 but adds to 5? 4 and 1? X plus 4 and x plus 1. So my x's are -4 and -1. And then it's important that we plug it back into the original and check and see if it works. Okay, so if I put -4 back in, and I have -4 plus 5 is under the root. And on the other side I had -4 plus 3, right? And so then I have root 1 is equal to -1. So 1 is equal to -1. That one does not work. Okay, so he's out. And so what if we tried the -1 plus 5, does that equal -1 plus 3? So root 4 is equal to 2. 2 is equal to 2. So that one is our answer.